All right, so in this slide, we're going to look at, or in this video, rather, we're going to look at bonding. Okay, bonding can be relatively complex, so we're going to actually have a couple videos about bonding throughout this unit. All right, so let's go ahead and jump in to bonding. Now, you'll notice here on the right that some chemical bonds are really, really complicated. Right, this is a very advanced structure. We're not going to be drawing anything nearly as complicated as this. However, by the end of this unit, we should be able to look at this and be able to tell a couple things, right? Like we should be able to say, oh, that's a double bond. This is a single bond, right? We should say, oh, there's a wedge, so that bond is coming out at the viewer. It's like coming towards you. Here's a hash mark bond. It's going away from you, right? There's an ion. It has a plus, right? So even though we're not going to be drawing anything nearly this complicated, hopefully by the time that we're done with some of this bonding, we'll be able to look at a chemical structure and at least identify a couple of its parts. Now, in order to talk about chemical bonding, we've got to talk about the Octet Rule just a little bit. And most of you probably know the Octet Rule already, but it is the answer to the question of why do elements bond? All right, the stability of an atom is solidified when its s and p orbitals, the valence shell, are full. So when you can get 8 valence electrons as an atom, you want that. You're willing to form a bond. The reason that we say the s and the p orbitals is because since the s block can hold 2 electrons and the p block can hold 6 electrons, you need the s and the p full to get 8 valence electrons. As long as your outermost valence shell is full, you're stable. Now, this is interesting for helium, right? Because helium is just 1s2. It is a noble gas. The only valence shell it has is s, and it's full. So that's why it's stable. Atoms will gain, lose, and share electrons to satisfy this rule. Gain or lose is going to be an ionic bond. Share is going to be covalent bonds. All right, and we're going to look at all of those. So here's a great drawing, a Lewis drawing of a bond. Here's another one that you might see in your textbook. In all of these cases, we can look and say, okay, hydrogen's happy with 2 electrons. Remember, it wants full s orbital, so it's happy with 2. Chlorine, though, now normally has 7. It gets that 1 extra. It has 8. It's happy. Oxygen here has 1, 2, 3, 4, 5, 6, 7, 8. So it's happy. Carbon has 1, 2, 3, 4, 5, 6, 7, 8. It's happy. 1, 2, 3, 4, 5, 6, 7, 8. So that oxygen's happy. So we're trying to satisfy the octet rule. We're trying to stabilize our outermost valence shell by filling it full of electrons. Now there's 3 kinds of bondings. We're going to look at a little bit of metallic bonding. We're going to really look at ionic bonding, and we're really going to look at covalent bonding. In ionic bonds, elements attract electrons away from other elements through what's called electrostatic attraction. Electrostatic means opposite charges attract. In covalent bonding, we have polar and we have nonpolar bonds, okay? And that depends on the electronegativity that the substituent atoms bring to the table. Covalent bonds are going to form when the electrons are pretty much equally attracted or mostly equally attracted. Now, with metallic bonds, and all we're really going to talk about with metallic bonds is this. The theory that describes how the electrons move in a metallic bond is called the sea of electrons. If you have 2 different metals bonded together, we call that an alloy. Alloys have different characteristics from their parent metals, right? So, bronze is made from copper and tin. Bronze is stronger than both copper and tin by themselves. It makes a better, metal for a sword or a shield. Iron, better than bronze. Steel, better than iron as far as like tensile strength and some things like that. So steel is an alloy of carbon and iron. Iron is obviously just an element. It's not an alloy. When we look at the characteristics of metals, we know that they're shiny, they're malleable, they're ductile, they're good conductors of heat and electricity. And the reason that they conduct electricity well is you have all of these electrons, and these outer electrons, they don't belong to any one specific metal. They just kind of float around in the sea. Well, if you put a positive and a negative charge on here, you can get those electrons to line up and, move in a specific direction, and that's electrons, okay? That's electricity, electrons moving in a specific direction. Now, that's really all we're going to talk about as far as metallic bonding. So you need a pretty basic surface level understanding of the sea of electrons for our purposes. Now, when we look at electronegativity's influence on bonding, we look at the value from the Pauling scale. And the Pauling scale is going to tell us whether or not we're making an ionic or a covalent bond. In order to figure that out, we need to find the electronegative difference. Remember from math, the word difference means we're going to subtract the big number minus the little number. So, or in this case, lower from the higher, right? Either way, same thing. If you get a number that is less than 0.5, you have a nonpolar covalent bond. We usually call this an NPC, nonpolar covalent. If the difference that you get is between 0.5 and 2.1, we call it a polar covalent bond. And if the bond is greater than or equal to 2.1, we have an ionic bond. So when we look at that, an ionic bond, the electronegative difference is so great that the electron is transferred from the cation to the anion, and we have the true ionic bond, two ions engaged in a bond. That's anything greater than or equal to 2.1. In a polar covalent bond, the electrons spend most of their time around the negative end of the molecule. This would be my more electronegative species, and they don't spend as much time around the positive end of the molecule, all right? So that gives you a dipole. In this case, my dipole would point this way, right? I have a partial negative on the left. If I have a pure covalent bond, we can see that the electron is spending the same amount of time around both of the atoms, all right? And since it's the same around both sides, well, then it's nonpolar. There is no dipole there. When we look at ionic bonding, some things that we're going to see, we're going to notice they form between a metal and a nonmetal, all right? And they're going to form as long as the electronegative difference is greater than or equal to 2.1. That's going to lead to a transfer, like we just said, and that transfer, just interestingly enough, is also going to lead to a change in size for the atom. So like a sodium atom is usually bigger than a chlorine atom, but when you take that electron away, it gets smaller, right? It loses some size, and the gaining of an electron for the chlorine, it gets larger. So typically speaking, when you look at the picture of an ionic salt, right, because any metal-nonmetal bond is called a salt, you'll notice that one of the atoms is usually larger than the other. The larger one is usually the nonmetal. Now, overall, they have a net charge of 0, unless you put them in water, right? They are soluble in water. Now, there are 7 properties of ionic compounds we want to make sure that we know. First, they are white, all right? They are white in color. They're crystalline solids at room temperature, okay? So at normal temperature, room temperature, right, 68 degrees Fahrenheit, you're going to have a solid white substance. It's going to be crystalline in nature. And crystalline means repeating patterns, okay? So in this case, we have green, purple, green, purple, green, purple, right? And the purple all line up and the green all line up. And, we alternate down the face, back and forth, back and forth, back and forth. But we have a very clear, right, set of patterns. They are brittle, and the reason that they're brittle is they have these cleavage lines, all right? So it's really easy for me to separate a salt crystal on those cleavage lines. They're non-volatile. We don't worry about leaving salt sitting on the table and it just exploding, right? Most of all of our ionic salts are considered non-volatile. That means they're not just going to up and react for no reason with the air. They're water soluble. If you put them into water, they're going to dissolve. They're going to disassociate is what that means. So the salt, right, I have NaCl. If I put it into water, it's going to become Na plus surrounded by water molecules, all right? you know, like so, and I'm going to have Cl minus also surrounded by water molecules. It's going to break apart. We'll talk more about that later in the year. They all have high melting points. Okay, I think salt's melting point is like 1600 degrees Fahrenheit, something like that. It's pretty high. And they are good conductors of electricity in solution. All right, that means they don't conduct electricity well when they're solids, but if you put them in water, that will actually conduct electricity pretty well. The reason that they will do that, right? If I look at, as far as their conductivity, if I look at this solid picture on the left, there's no good way for my electricity to move or to get those negative ions to line up. There's no way to do that. However, if I add a charge here, right, I can get these guys to line up pretty well, and the positive ions can just move out of the way. Okay, so make sure you know these 7 properties. Very important that you know them. That means like know them without looking them up. Now, what is dissociation? Okay, dissociation is how an ion or how an ionic compound behaves in solution. All right, and we're going to see that word in solution a lot. It means in water. So when you put a salt in water, the water actually attacks the salt. You can see that right here in this picture, okay? These water molecules are attracted to the salt because water is polar, okay? It's got, a positive end and it's got a negative end. And so the negative end right around oxygen is attracted to the cations, right? There's attraction here. And the anions on the salt are attracted to the hydrogens. And the water molecules surround those anions and those cations with what we call a hydration shell. It just means they're surrounded by water molecules. And it will literally break apart the salt when it does that. So this right here, you can see the hydration shell. You can also see it right there. Now notice, around the cation, the oxygens, the red molecules here, or the red atoms, are pointed inwards because the oxygen is negative on water and the cation is positive, so you have electrostatic attraction, forming, an interaction there based on charge. Up here on the top, you can see that the hydrogens are what's facing down towards that negative ion because they are positive and therefore, opposites attract. This is going to dissolve stuff. That's the essence of what we're describing here. So as these hydration shells form around the salt crystal breaks apart and it gets pocketed in between the water molecules and you dissolve things. So that's ionic bonds. Ionic bonds form between metals and nonmetals. There's transfers of electrons. Make sure you know the 7 characteristics and how it relates to dissolving in water. Now let's look at covalent bonding. Covalent bonding forms between 2 nonmetals. They form what we call molecular compounds. Depending on the electronegative difference, a covalent bond might be polar, might be nonpolar. Okay. Unlike ionic compounds, there are no predictable properties for covalent compounds. So there's nothing to memorize there. Just know that they don't have predictable properties. The unequal sharing of electrons is going to lead to some polarity. That is one of the few predictable things, right? We just look at the electronegative difference. If it's less than 0.5, hey, it's going to be nonpolar. If it's between 0.5 and 2.1, hey, this is going to be a polar molecule. All of the bonds in covalent bonds are considered electrostatic between the nuclei and the shared electrons. So the positive charge of the nucleus attracts those shared electrons into the bond. Electrostatic, again, means attraction between opposite charges. So let's look at water, right? A lot of things going on here with water. Number one, we have this delta negative, which means partial, all right? Water is a polar covalent bonded molecule. You can see that the electrons are pulled from hydrogen towards the oxygen molecule here, and that gives us some polarity. This is called an electropotential map. This image right here is. Red is indicating regions of negative charge. Blue is indicating regions of positive charge. And here you can see, from the pin to work, the electronegative numbers. So 3.4, the Pauling values, rather. 2.20 gives us 4 to 1.24. All right, so that is squarely between 0.5 and 2.1. So this would be a polar covalent bond, a PC bond. And when we look at polar molecules, if we just try to break that down into simple language, basically they're not sharing their electrons equally. Structure impacts function. So if you're not sharing your electrons equally, that's going to impact the function of the molecule, how it behaves. So polar molecules are going to be attracted to other polar molecules, and they're going to avoid nonpolar molecules. So oil and water don't mix because oil is nonpolar, water is polar. They're not attracted to each other. Okay? There's a term for that. It's called miscibility. That means able to be dissolved. And you can think about miscibility in the terms of like dissolves like. So polar things dissolve other polar things. Nonpolar things dissolve nonpolar things. When you have partial charges and dipole arrows on the molecule, that shows the direction of the negative charge. Okay, so here is CHCl3. Now you'll notice that there are 3 chlorine atoms on the bottom of this tetrahedral molecule. Chlorine is more electronegative than carbon. Carbon's more electronegative than hydrogen. So the electron in hydrogen is pulled towards carbon. That's what this arrow right here is showing us. And then the electrons around carbon are all pulled towards chlorine. So we can see that overall, the electrons are pulled downward. So that would be our dipole moment. Here in HCl, we know chlorine is more electronegative than hydrogen. If we did our electronegative difference, we'd find this is a polar covalent bond, and the electrons are being pulled that direction. Here's another one for you, CH2O. Oxygen has actually 2 lone pair electrons around it. It's more electronegative than carbon, which is more electronegative than hydrogen. So the overall pull is up towards those oxygen atoms. Same thing here for ammonium. All right, or ammonia, excuse me. You have a lone pair right there. Nitrogen is more electronegative than hydrogen, so everything is pulled towards the middle. So from the bottom to the top gives us our dipole arrow. Now, on the other hand, we have nonpolar molecules. They equally share their bonding electrons. So there's no region around the molecule that has an unequal amount of electrons. The electronegativity, right, is going to cancel out each of the 2 or 3 or however many atoms in the species. It's going to cancel out their pull. All right. So here we've got CCl4. Well, the chlorines are equally pulling everything in opposite directions, right? So they're all equally pulling out towards chlorine, so there's no net dipole. If you put nonpolar molecules in with polar molecules, they'll segregate, right? So think oil and water again, or Italian salad dressing, right? You shake it up, you get the, all the little oil bubbles, but if you leave it sitting, it will just separate itself. Polar and nonpolar things don't dissolve into each other, so the word that we use to describe that is immiscible. Here are some more just to look at, all right? They have no net dipoles. All right, so let's talk about Lewis diagrams real quick. Lewis diagrams tell us how many valence electrons an atom has, and it's how I drew all those pictures that I then added my dipole arrows to. A couple things to keep in mind. Number one, hydrogen and helium only want 2 electrons to be stable, but everybody else wants to have 8. That's the octet rule we talked about. If you know the number of valence electrons, you can predict how those bonds are going to form between atoms. There are 6 steps for drawing a Lewis diagram. All right, we're going to look at all 6 of those and then draw one. So first, you have to determine what atom goes in the middle. It's usually the element of which there's only one present. It's never hydrogen. Hydrogen can only have 1 bond, can't form more than 1, so it can't be the central atom. It's pretty much never a halogen. So group 17 guys, they're usually not in the middle. Not always, but usually. You're going to count the number of valence electrons that each atom in the formula has, and then add them up to figure out the total number of valence electrons that are available. We're going to draw the central atom. We're going to put the attached atoms around it as far apart as possible, kind of like dividing a circle up. We're going to attach those atoms by drawing lines from the central atom to the attached atoms. That shows their bond. A bond is worth 2 electrons. 1 electron from each species is involved in the bond. Then we're going to draw the dang dot diagrams, okay? So the dang dot diagrams show where the valence electrons are. This is going to complete the octet for all the attached atoms. I'll show you how to do that in just a second. Number 5, we're going to make sure we've used up all our electrons from our total list. If we have any left over, we put them in the middle, even if it breaks the octet rule. That's okay. If the central atom doesn't have 8 and you're out of electrons, then in that case, we're going to create double or triple bonds in order to share those electrons. That means we got to erase some of our dots and draw new lines. If there's a charge on the molecule, you put your whole Lewis diagram in a set of like square brackets, and you write the charge outside in the upper right corner. Hydrogen never gets dots. Keep that in mind. So let's do one of these. So here, we're going to draw sulfate, all right? Who's the central atom? Well, our rule tells us that it's probably the atom that there's only one of. So in this case, I have sulfur. I need to count up my valence electrons. Sulfur has 6. I know that because I count from the left to the right, just like we do for charge. So let's draw that out here real quick. So we have 1, 2, skip the D block, all right, 3, 4, 5, 6, 7, and then helium will give us 8. So there's my noble gases. All right, so sulfur, oxygen's here, sulfur is there. So as I count from the left, right, 1, 2, 3, 4, 5, 6, sulfur has 6 valence electrons. Oxygen also has 6. It's in the same column, but there are 4 of them. I know there are 4 of them because of that subscript right there. So that gives me a total of 24 electrons from oxygen, 6 from sulfur. I also have a charge of -2, which means I have 2 extra electrons. It's negative. That's how I know that they're extra. 6 plus 24 is 30, plus 2 gives me 32 total electrons. So now I need to draw the bonds, all right? And I need to complete the octet, all that good stuff. So let's, wait, do I not have that on here? Oh, there we go. We're going to do it one step at a time. So central atom is sulfur. I need to draw my bond. So I have oxygen, so I need to put them around the outside as far apart as possible. Attach them, all right, just like so. I need to draw the dang dot diagram. So I know that all of the attached atoms, because they aren't hydrogen, need to have 8 total valence electrons. So the bond is worth 2, so 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Well, I've now used all 32 of my electrons, right, of my total. 8 here, 8 there, 8 there, 8 there. 8 times 4, well, that's 32, okay? Oh, go back. What? No, stop. Get my eraser. Get rid of those lines. All right, the next thing I want to do is make sure the middle atom is good. Well, it's got 4 bonds. Each one's worth 2. 2 times 4 is 8. Sulfur has 8 electrons. It's happy. And so now, because it's got a charge, I put a bracket around it, and I write -2 outside, top right corner. And that's it. It's done. There's our answer. All right, let's do hydroxide. Who's the central atom? Well, there's only 2 there's only 2 atoms. So there is no central atom. It's linear, right? So I just draw the 2, O and H, okay? Count my valence electrons. Well, oxygen is in the same row that it was before. It's got 6. Hydrogen's in group 1. It's got 1, so that's a total of 7. The charge is -1, so I need to add an electron. That gives me a total of 8. I need to draw my bond. I need to complete the octet, so to draw the dang dot diagram. All right, all the attached atoms escape. I know not to give any to hydrogen because hydrogen never gets dots. It's happy with 2. So oxygen has 2, 4, 6, 8. It's good. All right. Hydrogen has 2. I'm good. I've used 8 total electrons. That's how many I have. I don't have any left over. So put it in brackets, put the charge outside. And there it is. Now notice, it doesn't matter which side that I drew oxygen on. Same thing either way. There are a bunch of these that we'll look at. Okay, so that's just kind of an intro to the Lewis diagrams. Probably do another video on that shortly. So look for it just for some more practice. If you have questions, let me know.